Good day, math learners! In this video, we will talk about independent event, dependent event, and conditional probability. What are independent events? Two events, A and B, are independent if the occurrence of event A does not affect the occurrence of event B. And how do we find the probability of independent events? The probability of two independent events, A and B, is equal to the product of their individual probabilities, denoted as P of A and P of B. And this is now the formula in finding the probability of independent events. So we have P, the intersection of A and B, is equal to P of A times P of B. Or in other words, the probability of the intersection of event A and event B is equal to the probability of event A times the probability of event B. Let us consider the first example. A coin is tossed and a die is rolled. Find the probability of landing on the head side of the coin and rolling a 6 on the die. So we let C sub 1 be the event of landing on the head side of the coin, and D sub 1 be the event of rolling a 6 on the die. Note that the occurrence of event C sub 1 does not affect the occurrence of event D sub 1, hence the two events are independent events. So let us now indicate the possible outcomes in tossing a coin. So we have head and tail, or H and T. And let us now identify its cardinality, or the number of outcomes in tossing a coin. So we have N of C is equal to 2. Since there are two possible outcomes, we have H and T. Then, for the event C sub 1, since we only have to choose the head side of the coin, therefore, we only have one outcome, which is H. Therefore, its cardinality is only equal to 1. Then let us also find the possible outcomes of D, meaning to say in rolling a die. So we have 6 possible outcomes. So we have 1, 2, 3, 4, 5, and 6. So its cardinality is equal to 6. And for D sub 1, wherein our event should roll a die, and it should be a 6. So we only have one outcome, which is 6. Therefore, the cardinality here is equal to 1. So to find the probability of the two independent events, so we have the probability of the intersection of event C sub 1 and event D sub 1 is equal to the probability of event C sub 1 times the probability of D sub 1. So we have here, so the probability of event C sub 1 can be computed as N, or the cardinality of C sub 1 divided by the cardinality of C, times for the probability of D sub 1, so we have to use the cardinality of D sub 1 divided by N of D, and substitute the values. So for the cardinality of C sub 1, wherein the event should land on the head side, so we have 1 over 2, since we have a total of 2 outcomes in tossing a coin, times we have 1. 1 here indicates that we only have one outcome in rolling a 6, over 6, and 6 here is the total number of outcomes in rolling a die. Then multiply the two probabilities, therefore, the probability of event C sub 1 and D sub 1 is equal to 1 over 12. Example number 2. A die is tossed twice. Find the probability of getting a 2 or 3 on the first toss and 4, 5, or 6 on the second toss. So let A be the event of getting a 2 or 3 on the first toss, and B event of getting 4, 5, or 6 on the second toss. Events A and B here are independent. First, we have to find the probability of A. So to find the probability of A, so we have here 2 or 3. So for the probability of getting a 2, so we have 1 over 6. 1 here since we only have one outcome in getting a 2, in rolling a die. Then 6 here is the total number of outcomes in tossing a die. Plus 1 here for getting a 3 over 6, the total number of outcomes. Then you add the two probabilities since this is an example of a mutually exclusive events. So we have here to simplify, that gives us 1/3. Then find the probability of event B. So we have here the probability of B. So we have 4, 5, or 6. So for getting 4, so we have 1 over 6 as the probability. Getting a 5, 1 over 6. Getting a 6, still 1 over 6. Then add their probabilities. Then to simplify, it gives us 1/2. Hence, to compute the probability of event A and event B, so we have to use this formula. We have the probability of the intersection of A and B is equal to the probability of A times the probability of B. Then substitute the values of each probability. So in the previous slide, we've learned that P of A, or probability of event A, is equal to 1/3 and probability of event B is equal to 1/2. Then multiply the two probabilities. Therefore, the probability of the intersection of event A and event B is equal to 1 over 6. Example number 3. A bag contains 6 red balls, 4 green balls, and 5 blue balls. One ball is taken from the bag, then replaced. Then another ball is taken from the bag. First question, what is the probability of getting a red ball on the first take and then a blue ball on the second take? Note that after a ball is taken, it is placed back into the bag. Hence, the first event, which is getting a ball from the bag, and the second event, which is getting a ball from the bag after replacement, are independent. So we let R be the event of getting a red ball, B event of getting a blue ball, G event of getting a green ball. Since the cardinality of R, which is equal to 6, cardinality of B is equal to 5, cardinality of G is equal to 4, therefore, to compute the cardinality of all balls here, we simply have to get the sum of the cardinalities of red, blue, and green, which is equal to 6 plus 5 plus 4, and that gives us 15. So to find the probability of getting a red ball on the first take and then a blue ball on the second take, we simply have to denote that one with the following. So the probability of the intersection of event R and event B is equal to the product of the probability of getting a red and probability of getting a blue. And that gives us 6 over 15, since we have the cardinality of R, which is equal to 6, and multiply that one with 5 over 15. Since the cardinality of blue is equal to 5, then the total number of balls is equal to 15. Then multiply the two probabilities and simplify. It gives us 2 over 15. The second question is, what is the probability of getting a green on the first take and another green on the second take? So in this case, we will use the notation, the probability of getting the intersection of event G, so meaning to say, getting a green on the first take, and another event G, which is getting another green on the second take, which is equal to the probability of getting a green on the first take times the probability of getting a green on the second take. So the cardinality of G here over the cardinality of all balls times the cardinality of G again over the cardinality of all balls. Cardinality of G is equal to 4, then all balls is equal to 15. Then you multiply that one with 4 over 15. Thus, the probability of the intersection between event G on the first take and event G on the second take is equal to 16 over 225. Example number 4. Find the probability of obtaining 2 heads on 2 tosses of a coin. So in this case, we have the probability of 2 heads is equal to the probability of getting a head times the probability of getting another head. So it gives us 1/2 times 1/2. 1 here, since we only have one outcome in getting a head, especially in tossing a coin. Then 2 because we have a total of 2 outcomes in tossing a coin. Then multiply 1/2 times 1/2. Then the probability of obtaining 2 heads is equal to 1/4. Dependent events. 2 events A and B are dependent if the outcome of the first event A affects the outcome of the second event B. And how do we find the probability of dependent events? The probability of 2 dependent events A and B, with the probability of A which is greater than 0 and the probability of B which is also greater than 0, is denoted as the probability of the intersection of event A and event B is equal to the product of the probability of A times the probability of B given that event A has happened. Let us consider this example. A box contains 4 white marbles and 5 blue marbles. What is the probability of drawing 2 blue marbles and 1 white marble in succession without replacement? The problem involves 3 dependent events. So, we have getting a blue on the first draw, then another blue on the second draw, and finally a white on the third draw. So those are the 3 dependent events in our problem. So let us now find the probability in getting a blue on the first draw. So we will denote that one as the probability of blue sub 1, which is equal to 5 over 9. So we are using 5 here since we have a total of 5 blue marbles, and 9 since we have a total of 9 marbles. You add 4 white marbles and 5 blue marbles, so that gives you 9. Second draw would be the probability of getting another blue. So after drawing one blue marble, only 4 blue marbles are left in the box. The total number of marbles becomes 8. Hence, the probability of getting a blue on the second draw is equal to 4 over 8. So blue sub 2 here denotes getting a blue on the second draw. Then for the third draw, which is getting one white marble, so after drawing the second blue marble, only 7 marbles are left in the box. Hence, the probability of getting a white marble in the third draw, given that the first 2 are blue, is equal to 4 over 7. So in this case, we still have to use 4 since the white marbles are still complete. Then 7 here since the 2 marbles are already taken. So the probability of getting the first blue on the first draw, we have 5 over 9. Blue on the second draw, we have 4 over 8. And white on the third draw is equal to 4 over 7. Therefore, we can come up with this formula. We have the probability is equal to the product of all probabilities. Then, substitute. So we have 5 over 9 times 4 over 8 times 4 over 7. Therefore, to simplify, the probability here is equal to 10 over 63. Another example would be, suppose you draw a card from a deck of cards, then without returning it, you draw another card. If you are interested to determine the probability of obtaining a jack of diamonds in the first draw and a spade in the second draw, how do you compute for the probability of this compound event? So we will denote the following. So let A be the jack of diamonds, B a spade. So the probability of A is simply equal to 1 over 52. 1 here since we only have one jack of diamonds. 52 since the total number of cards in a deck of cards is equal to 52. However, once that jack of diamonds is obtained, the sample space for the next event will decrease by 1. Since from the problem itself, without returning it, therefore we need to decrease it by 1. Has already been drawn. Therefore, there are 13 spades from 51 cards. So, the probability of B, given that the event A has already happened, is equal to 13 over 51. Therefore, the probability of the intersection of event A and event B is equal to the probability of A times the probability of B given that A has happened is equal to 1 over 52 times 13 over 51. And that gives us 1 over 204. Another example, 3 cards are chosen at random from a deck of 52 cards without replacement. What is the probability of choosing a king, queen, and an ace in order? From the phrase without replacement, the 3 events here were dependent of each other. In event 2, where the number of cards is only 51, because a card was already chosen from event 1. This similar observation can also be seen for the number of cards in event 3. However, you can observe that the n or the cardinality of the king is equal to the cardinality of the queen which is also equal to the cardinality of ace, which is equal to 4. Because in a deck of cards, we have 4 kings, 4 queens, and 4 aces. And these events are mutually exclusive. So to find the probability of this problem here, so we simply have to multiply the probability of the king, queen, and ace. Then we have first probability of getting a king, so it gives us 4/52. So we are using 52 here since we have a total of 52 cards. For the probability of getting a queen, as you have noticed, it is just 51 since in our problem it should not be replaced, so we have to decrease it by 1. So for the probability of getting a queen, it gives us 4/51. Then for the last card, which is the probability of getting an ace, so in this case we have to use 50 since another card is taken. Then after which you multiply the 3 probabilities and simplify. Therefore, it is equal to 8/16,575. Conditional probability. The conditional probability of an event refers to the probability of that event on the condition that another event has occurred. The notation P, B, A, which is read as the probability of B given A, represents the probability of event B occurring on the condition that a first event A has already occurred. So to find the probability in this kind of event, so we will be using this formula. So the probability of B given A is equal to the probability of the intersection of event A and B divided by the probability of A. And we have to make sure that the probability of A should not be equal to 0, because if that would happen, it becomes an undefined answer. So let us consider this example under conditional probability. An action research shows that 25% of the CSE test takers failed the test on the first try and failed again on the second try. Of these takers, 40% failed the test on the first try. What percent of those who failed the first test also failed the second test? So we will denote the following. So let A be the event that CSE test takers failed the test on the first try. Event B, event that CSE test takers failed the test on the second try. Then we have A intersection B, be the event that CSE test takers failed the test on the first try and failed again on the second try. So we will be using this formula. So the probability of event B given A is equal to the probability of the intersection of event A and B divided by the probability of A. And that is equal to 25% divided by 40%. Which is equal to 0.625, or in percentage, it gives us 62.5%. Therefore, 62.5% of the CSE test takers both failed the first test and the second test. Another example would be, a box contains 10 balls numbered 1 to 10. two balls are drawn, and one of the balls shows the number 7. With this condition, find the probability that the sum shown by the balls is 12, 13, or 14. So first, we have to consider the sample space in drawing two numbered balls, and these are the following. So we have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, 10, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2, 9, 2, 10, 3, 3, 3, 4, 3, 5, 3, 6, 3, 7, 3, 8, 3, 9, 3, 10, 4, 4, 4, 5, 4, 6, 4, 7, 4, 8, 4, 9, 4, 10, 5, 5, 5, 6, 5, 7, 5, 8, 5, 9, 5, 10, 6, 6, 6, 7, 6, 8, 6, 9, 6, 10, 7, 7, 7, 8, 7, 9, 7, 10, 8, 8, 8, 9, 8, 10, 9, 9, 9, 10, and 10, 10. As you have noticed, we have not included 2, 1, and the rest of the numbers, since, like for example, 2, 1 is just the same with 1, 2. And in the given problem, it is not specified that the order of each number matters. So that's why we did not include 2, 1, 3, 1, 3, 2, and the rest in the sample space. So the cardinality of our sample space is equal to 55. After identifying the sample space in the given problem, so we will denote the following. Let A be the event that one of the balls shows the number 7. So first, we have to list it down. We have 1, 7, 2, 7, 3, 7, 4, 7, 5, 7, 6, 7, 7, 7, 7, 8, 7, 9, and 7, 10. Then its cardinality is equal to 10. Let B be the event that the sum shown by the ball is 12, 13, or 14. So we have the following: 2, 10, 3, 10, 4, 10, 3, 9, 4, 8, 4, 9, 5, 7, 5, 8, 5, 9, 6, 6, 6, 7, 6, 8, and 7, 7. Thus, it gives us the cardinality of this event, which is equal to 13. So why did we use 2, 10 here? So we are using 2 and 10 since when we add 2 and 10, it gives us 12, which is part of our event B. 3 and 10, it gives you 13. 4 and 10, when you add, it gives you 14. 3 and 9, it gives you 12. Then so on and so forth. Then we also denote the intersection of A and B. Be the event that one of the balls shows 7. So in this case, we have to list down the intersection between these two events. So we have 5, 7, 6, 7, and 7, 7. So thus, it gives us the intersection of A and B, which is equal to 3. And then, we will use the formula. The probability of event B given A is equal to the probability of the intersection of event A and event B divided by the probability of A is equal to 3 over 55 divided by 10 over 55, which is equal to 3 over 10. And to simplify that one in decimal form, it gives us 0.3, or in percentage, 30%. And that ends our discussion on independent event, dependent event, and conditional probability. Thank you.